Okay, so in this video, we're going to talk about the integral test for infinite series. So just a fact to kind of get this started. So a series of non-negative terms converges if and only if its partial sums are bounded from above. Okay, so using this fact, let's consider the harmonic series. So the harmonic series, this is the harmonic series, by the way. The harmonic series diverges. And so using this fact, we can actually see kind of what's happening here if we really look at what's going on with the sum. So I start with 1, and then I have 1/2. So I'm already at 3/2 right here, right? And what I just want to point out here is, so in the first, in the third and fourth terms, this sum is greater than 1/2. And then, as we continue on, this part of the sum here is greater than 1/2. And if I wanted to continue this on from terms 1/9 to 1/16, this is also greater than 1/2. So you can see here that this is actually kind of slowly growing. We're like slowly adding on more terms of 1, even if it's slowly. So this series is just kind of continuously getting larger and larger with these terms. And so one thing that we can do with the harmonic series is the partial sums from this fact can be shown that they are going to be greater than 2 to the k over 2. This is a number that is bigger than 1. And as we know, if you have some number that is larger than 1, then very often your series will diverge. So the harmonic series diverges because these partial sums, they're not bounded from above. If we can view this as a number greater than 1, it's not bounded from above. It's just getting slowly bigger and bigger. And so a more efficient way of being able to determine whether something is bounded from above or not is to actually use what's known as the integral test. So the integral test basically is now relying on integrals, which, ultimately kind of have this connection to area, right? And we know that partial sums have this connection that we can represent with area. So we can use integrals as a more efficient way to kind of look at this, besides doing this long, analysis of like, oh, what do these sum to? What could the partial sums be? We can use an integral test to basically suss out what's going on with the partial terms. So here's what the integral test says. Let's say we have a sequence of positive terms. So we're going to represent that sequence as f of n. So f has to be continuous, positive, and decreasing for all n greater than or equal to n, so some positive integer. So at some point, this function has to get to a point where it's going to be continuous, positive, and decreasing at some point. When that happens, when those conditions are met, then we say that both the infinite series and the integral that goes from n to infinity, these either both converge or both diverge. So this doesn't mean that they're equal to one another, but the sums work in a similar sense. And so if one converges or diverges, so will the other. Now I do want to highlight here, so we do have to have that our sequence has to have positive terms, right? So that rules out certain sequences. And the other thing that you have to be able to prove to use this test is that your function is continuous, positive, and decreasing after some point. And so this condition here can be a little bit of a bear to work with sometimes. But if you get that, then you can go ahead and use this. Okay, so let's talk about a series that maybe we can like pretty easily tell just from looking at it. So I'm going to ask, does this series converge? Okay, so I've got 1/n squared. Well, first of all, this is definitely going to be positive because all the terms are squared. It's definitely going to be decreasing as we go along because the denominator is just increasing. So, and then it's also continuous from 1 to infinity. So it's not continuous at 0. So some of these you can tell just by looking at it and reasoning your way out that, yeah, it definitely meets the conditions. And so when that happens, using the integral test is nice and easy peasy, because what I can do is I can set up this integral 1/x squared dx. So I'm just going to evaluate this. Now, we've talked about in other videos how to evaluate integrals that have infinity in the bounds. So what you do is you set up a limit, and then we reset this up to be 1 to b, and then we evaluate as b goes to infinity. So this will be x to the negative second dx. Okay, so now if I integrate this, so I'm going to get negative 1 over x. Oops, sorry, I forgot about the limit, my bad. The limit as b goes to infinity, negative 1 over x from 1 to b. Okay, cool. And so then this turns into the limit as b goes to infinity, negative 1 over b minus negative 1 over 1. So the limit of as b goes to infinity of negative 1 over b, that's going to be 0 plus 1, so this equals 1. Okay, and so since the integral converges, we know then that the sequence will converge. So yes, it converges by the integral test. We'll just write integral test. Okay, so that's what we're looking for. Now, the sum is not equal to 1. It's just that this sum converged to a number, therefore the sum itself will converge to something. Okay, so we can extend this logic to a p series, which is 1 over n to the p. Okay, so let's figure out what values of p this will converge at. So we will do that by setting up the integral. And then after we set up the integral and kind of evaluate it a little bit farther, we can kind of go from there. So I'm going to make a little space, and obviously in setting up the integral, I need to set up a limit here. So remember, this is x to the negative p. So if I evaluate this, so I'm going to ultimately have 1 over negative p plus 1, and then this is going to be let's see, negative p plus 1, and this is going to go from 1 to b. Okay, so we have a lot of letters running around here. But okay, so now I want to set up this limit. And what I would actually encourage is for you to just see how far you could take this and evaluate this before I tell you, just to see if you can come up with your own answers of what p would have to equal for this to converge. But I'm going to go ahead and keep going with this. So I'm going to have the limit as b goes to infinity. This is going to be 1 over 1 minus p. We'll just write it like that. And then I'm going to go ahead and plug in. So this is going to be 1 over b to the, let's see, to the p minus 1. So just keep in mind, if on top this was negative p plus 1, to send it back to the bottom, this becomes p minus 1. So just keep that oriented. And then all of that minus, so this will be 1 to the negative p plus 1. So this will just be 1. So we're just plugging in 1. Okay, so now I have to think about when is this going to converge. And so basically what I want to have happen here is, so if you think about this, I need b to not end up in the numerator again, right? So what I mean is, so let's pretend that p equals negative 1. So if p equals negative 1, right, so then this would become b to the negative second. So this would be b squared. And then the limit as b goes to infinity, this is obviously going to end up going to infinity. So I have to think about what values are not going to create a negative exponent here. If I get a negative exponent, then this whole thing moves up. And so that's all going to happen then around 1, right? So I need p minus 1 to be greater than 0, really. And that will happen when p is greater than 1. If p equals 1, well, then we have the harmonic series. And so we already said that's a problem. And if p is less than 1, so if p is anything less than 1, then this is going to end up becoming a negative number, right? So these are all going to diverge. So what that means is when p is greater than 1, this series converges. And if p is less than or equal to 1, this will diverge. This diverges. Okay, so that now becomes a fact that we can use. So we actually don't even necessarily need the integral test for this because a p series is so well known. So just if p is greater than 1, it's going to converge, and if it's less than or equal to 1, it's going to diverge, and that's by p series. If it equals 1, it's a harmonic series, so we know it diverges. So yeah, but we are able to use the integral test, right, to help us with that. Okay, so now let's take a look at 2 more examples of the integral test. So for this first one, so I want to use the integral test here, but you'll notice that in turning this into the function, so in turning this into the function, let me just turn it into the general function first. So the value of x here matters, right? And you could say, oh, well, this is clearly going to be positive, right? Because a series is just putting in positive terms. So, okay, that's good to go. So remember, we need positive, we need it to be continuous. So it's definitely going to be continuous for all terms because this is n squared plus 5. So this denominator will never equal 0. So, okay, so we're positive and continuous. But I think the one part that's maybe not obvious in setting up this integral is this decreasing. And the answer is it actually depends on the values that you choose. So actually, if you plug in, you can tell just by looking, right? If I were to plug in 0, if I plug in 0, then this whole thing will equal 0. And if I were to plug in 1, I get 1 over 6. So technically that is increasing there, right? And if I were to plug in 2, so let's see, what do I get for 2? For 2, I get 2 over 9. So this is actually increasing for the first few terms. So that's one of the things that you have to watch out for with this test. So you can't just be like, oh, it's positive and continuous and I hope it's decreasing. You're going to have to figure out where it's decreasing because that's going to influence your limits of integration here. And so if you aren't sure where it's increasing or decreasing, then you have to go back to the good old first derivative test. So if I let my f of x be this function here, so just pretend that it's all x's, I do need to take the first derivative. And the only way to take this first derivative is from our old friend, the quotient rule, right? So I take the derivative of the top times the derivative, or leave the bottom alone, and then subtract off the top. I'm sorry, I should make these all x's. Brain's at like half capacity for some reason today. And then this is 2x. Okay, so here's the top part of my derivative, and then divide that all by the bottom squared. Okay, so this then, let's see, this is going to be negative x squared plus 5 over x squared plus 5. So now I just need to determine when is this increasing or decreasing. And so the way that you do that is you set the denominator equal to 0. So I've got 5 minus x squared. I can set it equal to 0 and I can find my critical points, right? And actually, this is going to be helpful. You can pretty quickly figure out where it's increasing and decreasing from this because what you're going to find is my x squared equals 5. So my x is going to equal plus or minus the square root of 5. Okay, so the square root of 5 is bigger than 2, right? And it's smaller than 3. So if you just think about this now, 5 minus x squared, anything larger than the square root of 5 is going to end up being negative. So if I plugged in, say, the square root of 6, what would I get? I would get 5 minus 6, that would be negative. So we need this derivative, right? We need it to be negative. So remember, you're decreasing if f prime of x is less than 0. And so this will be decreasing for x greater than or equal to the square root of 5. So anything greater than the square root of 5, you will get a negative number on top, and so that will make the whole thing negative because the bottom always has to be positive. Now, if you need to go back and review the first derivative test, I do have videos on that. I'm going to assume that you know that here because otherwise this video is going to be very, very long. So, okay, anyways, so now what do I do with this information? This would not make sense to use in my integral, right? Because remember, if we go back to the integral test, we did say that this has to be greater than an integer. And so now I need to think of like what is the closest integer to this. So really, for our purposes, for any bit x greater than or equal to 3, we are going to be good to go, right? So for all values greater than or equal to 3, we're good. So now that helps me set up my actual integral. So I'll make some space. So my integral is going to go from 3 to infinity, and then I just set up the rest of this, x over x squared plus 5 dx. So now we've got to integrate the whole thing, right? And so to integrate, let's see, I'm going to integrate first the indefinite integral. So I'm going to let my u equal x squared plus 5. My du will be 2x dx. So 1/2 du is going to be all settled. So like I said, I'm going to start with the indefinite integral. So I'll bring that 1/2 out in front. So I have du over u. So my indefinite integral is the natural log of u. And now I need to set up a limit. So I'm going to set the limit as b goes to infinity of 1/2 times the natural log of x squared plus 5. By the way, I can drop the absolute value because this is guaranteed to stay positive, so I don't have to worry about the absolute value in this case. And so then my limits of integration are going to go from 3 to b in this case. And so then we have to evaluate this as b goes to infinity. So then if I set this up, I will see, so I have 1/2. This is going to be the natural log of b squared plus 5 minus the natural log of, what is it, 14? Yeah, 14. Okay, so as b goes to infinity, this thing is just going to end up exploding. So this actually is going to equal infinity. So the integral diverges. And so since the integral diverges, the series diverges. So as you can see, some of these are going to have some real work, even with just your kind of basic, so to speak, integration and some things that you do have to remember about how the functions work. Okay, so for this one, so the good news with this next one is that we have this much more straightforward denominator. So we just have a 1 on top, and then we're going from n equals 2 to infinity. So all of these values are going to be positive, continuous, and also decreasing because this is just one fraction with just something in the bottom. So we're good to go on not having to go through all the work to check like, okay, what do I have to set up for my limits of integration? This thing's just always decreasing. So some of these are easy to pick out and some of these are kind of tricky and you're gonna have to do some work. So what I want to encourage you to do here is, so we're gonna have this integral and I want you to determine whether the series converges or diverges. And I'm actually going to just suggest you pause here and give it a try and then hit play when you're ready. Okay, so once again, this is going to end up using another bout of substitution. So in this case, I'll just tell you the pieces that you should have used. I'm going to skip over the rest of the substitution just for the sake of time. So in setting this up, you can use these parts for your substitution. And so ultimately what you're going to get is you're going to get an integral. So you should get -1 over the natural log of x. And we're going to evaluate this from 2 to b, and then b, of course, goes to infinity. So I'm going to have the limit as b goes to infinity, -1 over the natural log of b plus 1 over the natural log of 2. And so now this part goes to 0 because the denominator is just going to keep getting bigger and bigger, so the overall fraction is going to 0. So this equals 1 over the natural log of 2. So the integral converges, therefore the series converges. So the series converges. Now we don't want to say it converges to this number, we just know that it converges. So that's all we can say. Okay, so I do have more videos on this topic with other examples, so I'm going to leave it here, and I will catch you guys in another video. Bye for now.